The final example I'm going to work at linearizing and analyzing data is the real-world example number 6. It's already written in your book, so you can follow line by line of what they did. And the reason I'm choosing this one is because it gives us a little different flavor because it's exponential model. I haven't done that yet, and the other example they give me to do is not. So this is all for variety's sake, and this model is probably the more difficult model to convert back, so that way I can describe how they were doing that. So clearing, hopefully clearing. First of all, I want to make sure we have the right data in our calculator, and I just will clear that list. Yes, clear. Okay, a little bit of variety here. The years went from 1990 all the way up to 2006, so I typed in, starting with 1900 as my base, so I'm going to let our x value start at 1900, the year 1900. That means 90 years later the salary is 354, 95 years later it was 584,000 in thousands in the year 2000, and so on. So it's a little unique thing here of representing these using 90s instead of 1990 and so on. Makes your numbers a little bit more manageable and easier to work with. So got the information in the calculator. What we want to do is we want to do a transformation. Now they're saying find an exponential model. So this should be modeled well by an exponential scatter plot. So go into the scatter plot. Let's get rid of this stuff here for the moment. And let's make sure you got the right plot being done. Second, stat plot. Plot 1 says it's going to do a scatter plot, list 1, list 2. Perfect. We got to make sure we get a decent window. The window that I'm going to choose, since the years are from 1990, which is 90, all the way up to 2000. What was our year? 2006, and we want to do a prediction of 2012 eventually. I'm going to go up to 120 years later. That gives me plenty of room. It wouldn't have to go up that far, but that's going to work. Our salaries go from 354 up to 1700. So to make the Y's fit on our scale, I went from 330 to 2000, went by 100s. And what I'm going to show you is a scatter plot of the salaries of the football players from the years from 1990 up to 2006. Now they're saying that this is an exponential model. That's not hard to believe. It looks like the salaries are increasing at an increasing rate. It looks like it's starting to tail upward and increasing faster and faster. So thank goodness for television advertisements and pro athletes getting huge salaries for this. Nonetheless, here's our data. We're supposed to linearize this data. In order to linearize what we think is an exponential model, which they're telling us we believe it is, we've got to go to our stat, we've got to edit, and we got to go over and transform our data. Now to do the appropriate transformation, if you think it's an exponential model, it is to take the logs. So I'm going to hit, notice I got L3 highlighted, hit enter, and then you want to do the natural log of your Y values, which are on list 2. So I'll go second, natural log of list 2, enter, and now what we're going to have is a transformation of all the Y values into the log of the old Y values. Take a good look at those. It's going from basically 5 to 7.4. So when we graph these, our linearized data, it should only go from 5 to about 9. So I'm going to go ahead and grab that window right away so I don't forget it. The X values should not change. We didn't transform those at all. We did transform the Y's, and as we said, those go from about 5 up to 9. So maybe go from 5 to 10. Go by, what the heck, 1 or halves. That'll split it up a little bit. And now I want to go tell the calculator I want to see my scatter plot of my transformed data. So I'm going to edit plot 2. I want to turn it on. Got to make sure that you have the right lists. The X's are in list 1. Yep, that's true. In our Y list, our transformed Y values are in list 3. Yep, that's right. I'm going to use the plus signs to mark it. And this is what I'm going to, oh boy, I didn't want to do that. Okay, maybe I want to do this then. Second, list 1. Okay, then let's take a look at our graph. Okay, here's our new scatter plot of the linearized data. It's believable that this graph has been linearized. It looks like the points are now more in line than they were before doing the exponential curve. This is what we want to run our linear regression on. So first thing we do is we linearize our data with the appropriate transformation. Then we go back and we hit our stat. We ask it to calculate a linear regression this time. So that's number 4. Hit enter. Are our data points that we want to linearize in list 1 and list 3? Yes, they are. That's where my transformed data is. Original X's, list 1, transformed Y's in list 3. We want to store this in. Sure, let's go back and let's store it in our Y vars function, Y1. Isn't that special? And then we hit calculate, and it's going to tell us what our equation should be. So in the y equals ax plus b format, so y equals ax plus b format. Remember, we transformed the y's. The y transformation was taking the natural log of your y values. We'll need that. But now I'm going to grab the data. And just a word of warning, whenever it's an exponential equation, don't round off too quickly. The old book that we had said always round to the 10,000th place. I don't think that's a bad piece of advice. So rather than just point, I got to get this down right. So I'm putting in a value for A, and it's going to be 0.0957. 0.0957. I want to double check myself. Okay, to 4 decimal places. When you do exponential models, because exponentials change so rapidly, small changes in this value that I just wrote down will make big changes in your exponential model. So that's why I'm rounding to the 10,000th place on this one. And for B, B is negative 2.7536. So, oh, I'm never going to remember all that. So what do I got to do here? Negative 2.753, 2.753, and I just wanted one more decimal place on that thing, and which would be a 6. And that was a negative, so plus a negative. That just fixed that. Now, this represents our equation for our transformed data. That should have been stored in our equation editor, and I don't think I ever went back and graphed that, our y equals, so that whole thing is stored in there. If I graph it, it should go through those points and fit pretty well. So our calculator did the least squared, the sum of the least squared regression line, fit the curve well, and that's what we have. The hardest part of this problem, and this is where it takes the most diligence and work, and that is to transform this back into the original model. So in the whole scheme of things, we were supposed to find an exponential model. We transformed the data, we linearized it, which meant it was an exponential model. So we have to fit it into this form, a times b to the x. This is our expo model. Let's try expo model. So when we get done, this thing has to be transformed into a model that looks like this. So how do we do it? Well, what did natural log, or what did y hat represent? That was a natural log of y. So I replace with natural log of y. These values remain the same. Now I'll just put in the minus 2.7536. We want to solve this for y. So to solve for y, we exponentiate both sides to a base e. That'll reduce, so y equals e raised to the power of 0.0957x minus 2.7536. Now, here's the thing. Does this look like that? Well, at this point, no. We've got to do some transformations to this. The transformations that we're going to use are using your exponent rules. So you got to think of your exponent rules. You have 3 rules. You've got a product rule, you got a quotient rule, and you have a power rule. We're going to use 2 of these. I'm going to get it set up so we use product and power. Here's what I do, so I use product and power each time. Y equals e to the 0.0957x. I can always write subtraction as adding the opposite, so 2.7536 with a negative. Now, by using that, I'm going to talk to you about this product rule. Here's what we have. If it's b to the n times, let me write this again, b to the m, n times b to the m, it equals b to the n plus m. So when we multiply like bases, we add the exponents, and that's what we have right here. This is really the stage that we're in right here. We have one base. It's base e. This base e is being raised to an exponent, which is being added together, which means we can rewrite it into this form here. So applying that rule, the product rule, I can write this as e to the 0.0957x times, that's really important, it's multiplication, e to the negative 2.7536. Right now, this, I have to get you to recognize that this is nothing more than a constant, and this constant that we're going to get is going to represent our value of a. So at this point, I'm just going to leave that, and then I'm going to come back and calculate it in a second. Now we want to focus on this part of our expression. We want it to look like a single base raised to a power of just x. Well, we have a single base of e, but we're raised to something times x. I don't want that something times x there. I just want a number raised to the x. So here's the rule that we're going to apply, which is the power rule. With the power rule, it's like this. If you have b to the n raised to the m, we write it as b to the m times n, or n times n, it doesn't matter. So this is the stage that we're in. We have a single exponent, a single base raised to a product of exponents. Here's our single base e raised to a product of exponents. So we're going to apply this and turn it into something like this. We're going to make this e to the point 0.0957, and then we're going to raise it to the power of x times e to the negative 2.7536. So I've applied the product rule to that exponent, and I've applied the power rule to that exponent, and now I'm in position to use the calculator to go ahead and get those constants. So I'm going to run, the first one I'm going to run is this e to the negative 2.7 blah blah blah. So second quit. Let's go and get second natural log, which is our e to the x. We need a negative 2.7536. 7536. Enter. And I want to keep several digits of precision here. I'm going to go 4 places, so 0637. So 0.0637. Now multiplication is commutative, so I'm going to put that first. I'm going to put this second, so it starts looking just like the rule that I have up here. Y equals a times b to the x. Now this is your value of a. Times, we need a b. The value of b is going to come from the calculation of this, e to the point 0.0957. So second natural log, and we've got e to the point 0.0957. 0.957, enter, which is 1.1004 times 1.1004, and that's raised to the power of x. So now we've got this in the form of a times b to the x, which is the form of a exponential equation. So this, hopefully, after all that work, is going to model the original data well. Okay, so what I'm going to do is I'm going to come back into the equation editor. I'm going to place that new equation in to y sub 2. I really don't want y1 graphed anymore. That was the model that fit our linearized data. So we're going to type in 0.0637. We got to take that times, and then I've got 1.1004 raised to the power of x. There's our exponential model. Enter. Now this is supposed to model the original data well. The original data was in plot 1, so I'm going to take off plot 2. It's been a while, so I can't remember what was in plot 1. Yes, it's list 1, list 2. I got to go back and set the window back. The x's should be fine. It's the y values that we transform. I'm going to change those back to 330, and it went up to $2,000, the salary, and that we'd probably want to go by at least 100s, and we'll graph. And with any luck, we're going to see, and it's looking good. We've got a curve that matches our original data well. Now this curve can be used to model the data, and now we can make predictions. So this is what we did in our first part of our investigation. I'm going to hit trace. I found the model. I put it in y sub 2. Here's our exponential model. So how many years after 1900 is it? We were supposed to go to 2012. So that would be 112 years later. So I'm going to type in 112, hit enter, and it's telling me that the salary is predicted to be 2,869. So let me write that down. 2,869. 2,869 thousands. So if I'm thinking right, then that should be in thousands. 2,869 thousand. So they're going to be making, does that seem about right? About $3 million, the professional athlete in any given year. So some of the top athletes are making more than that right now. Some of the athletes are making less than that. But on average, I think that's probably a pretty good predictor of what our sports heroes and all-stars are making, especially in the NFL there. So, all right, some different challenges in that problem. I hope that you watched the video and you paid close attention to these exponent rules, because that's typically where we've had trouble before, getting it broken down into this exponential model, and that is what the requirement is. That's as quick and fast as I did. Please don't hate me. I'm trying my best. Have a good time with these problems.